idea of Verilog or VHDL? It was there. Was there in your academic syllabus during your BTech? During your BTech, have you gone through this subject, Verilog HDL or VHDL? I think lab might be there, right? ICA, VLSI lab or IC lab. Yeah, VHDL. Okay, VHDL. Verilog idea on the everkaina? Do you have anyone is having idea of this Verilog? Okay, it's no problem. Okay, no problem. No problem. And okay, so we will be normal as per the industry standard. Verilog is the most important thing. VHDL, I think nowhere it is used actually. So why? Because Verilog is having its own benefits, more and more benefits than VHDL. Actually, the evolution of this ASIC design, uh, in the process of this evolution, it has started with the VHDL only. So, but after later on, Verilog came into existence after VHDL. So it is having more importance. It is having more advantages than VHDL. So that's why in industries, everyone will go for Verilog. Uh, maximum industries they go with Verilog coding only. So as see, let me stop the screen sharing and I will start recording the session. I think session is being recorded. Session is being recorded. So now are you able to see a Microsoft Word document? Are you able to see Microsoft Word document?
Yes, ma'am.
Yes. Okay. So here we'll start. So to make it easier for you. So in our session today, we will be talking about VLSI and also about, this is our first point of interest, and about ASIC design flow. ASIC design. Okay, we will be focusing on VLSI. You all know what is VLSI, right? Okay, it is very large scale integration or integrated circuit design. Okay, very large scale integration or integrated circuit design. So what do you mean by integration? What do you mean by integration? Integration is nothing but arranging all the integration means, so bringing all the things together. Okay, integration is bringing all the things together on a single platform. It is nothing but integration. Okay, so in a large scale, you are integrating, that is in the large scale, the components are integrated in a large scale, that is called as components are integrated in a large scale, that is called as large scale integration. Okay, so the components are integrated in a very large scale, that is called as very large scale integration. Actually, what are these components? Let us suppose this is the platform. Okay, let us suppose this is the platform. On this platform, I am integrating many active and passive components. Okay, so if you see, you might be remembering your EDC lab, right? On EDC lab, we used to bring the transistors, resistors, capacitors, all the things onto a breadboard, right? Okay, breadboard is the platform. Okay, breadboard is the platform that we have integrated the components. Okay, so now here we are taking a chip, or it is called as we are taking a chip, or it is called as die, DIE. Okay, die or chip, or we call it as an IC. We call it as an IC after integration. So we are taking this. This is our platform, which is nothing but the chip. On this platform, we are integrating the passive and active components. Okay, I need not tell you what are the active components and what are the passive components. Okay, resistors, capacitors, diodes, transistors. Okay, among this you can divide active and passive components. Okay, so all the components we are integrating on the same single platform. Okay, so today, see, today if I am able to integrate, let us suppose today if I am able to integrate 20 components on this single platform. Okay, today if I am able to integrate 20 components on this single platform, after 2 years or after 18 months, on the same platform, I am able to integrate 40 components. Okay, so today is this year is 2022. Okay, in 2024, on the same chip, I am going to integrate 40 components. Okay, and again in 2024, if we suppose 40, if you are doubling that 40, 80 components I am able to integrate. Okay, so that is ante for every 2 years. Okay, so if I tell you exactly, for every 18 months, every 18 months, the number of components on the IC are doubling. Okay, the number of components on the IC are doubling. Okay, I just gave you an example. నేను ఒక చిన్న example మాత్రమే ఇచ్చాను నేను. Okay, but in real time, so now millions of components. Reality lo చూస్తే, if we take our cell phone, in the cell phone, if you take single chip, okay, that is SoC. Okay, on a single chip, millions of components, that means millions of transistors are being integrated on a single chip. That is present scenario. Okay, actually, why this VLSI came into existence? We should know about the history of VLSI. Okay, we should know about the history of VLSI. So let me um, show you on this. Just to see this. So actually, the very first technology was vacuum tubes, right? Are you aware of vacuum tubes? We have studied, right? The very first technology was vacuum tubes. So there were no transistors, nothing were there. So vacuum tubes tarvata, we have vacuum tubes tarvata, we have point contact transistor was there. Okay, point contact transistor was there. Okay, so like this, if we have next point contact transistor tarvata, an IC was made with 2 transistors. Okay, we used to call it as flip-flops. Okay, so integrated. Are you able to see, ma? Are you able to see? Screen మీకు కనిపిస్తుందా నేను రాసేది? Yes. Okay, so if we go to the history, అవసరం ఉన్నాయి మాత్రమే చెప్తాను. If we go to this history, vacuum tubes నుండి స్టార్ట్ అయ్యి, so diodes వరకు, starting from the vacuum tubes, till diodes వరకు అంటే it was like what existence. If we first, if I tell you, the very first computer was made up of vacuum tubes. It occupied a what larger area, more than a very big room it has occupied. And also the memory was very less, RAM was very less, ROM was very less, operating speed also was very less. All these things we have studied, we need not go for that. Okay. So after first, what if we talk about the transistors? If we talk about the transistors, so first thing is before before the MOS was existed, so BJT was existed. Okay, bipolar junction transistor. If we see the devices, if we see the devices, 1960s or 1970s, if we see the devices, so there were no electronic devices actually. Okay. So during that time, the electronic devices were only if a family was having a radio, that was also the huge size radio that occupied so much of space. It was a great thing. Okay. So only what scientists or no, people were knowing only about the BJT. Okay. So see, if you design any device by using the bipolar junction transistor, if you design any device by using the bipolar junction transistor, so first thing is size is very heavier. Size is the main drawback. Okay, size is the drawback for the BJT. Okay, before the existence of MOS, BJT, using BJT only, the what electronic devices were used to be fabricated. The main drawback is size is the drawback, and also bipolar junction transistor, they occupy more power. Okay, so power consumption was more. Power is also a drawback. Okay, power also you can take it as a drawback. Size, power, and also what power consumption will be more, and power dissipation also will be more. But in terms of speed, power no, power consumption is more. Okay, uh, they consume more power. And also what coming to if we talk about the speed, performance is very good. Okay, if you performance wise, very good. So later see if they are performing good. Okay, and reliability wise also BJTs are very good. Okay, so if they are performing very good and if the reliability is more, and but if the power ఈ రెండు advantages ఉన్నాయి, even though BJT is having these two advantages, there are more advantages with BJT. Now I'm talking about performance and reliability, which are very important. Speed of operation is also very good. Just excuse me, I will just do that. Sorry. Uh, if we talk about reliability and performance, main factors are reliability, performance, speed, performance ante, so speed comes under this performance only. Okay, so if the speed is more, we can say that it is giving good performance. Though it is having these two advantages, advantages, the main drawback is size. Okay, power consumption is a part. Power consumption is also very important, but the size is the drawback. Always we cannot size is a drawback, and also we cannot carry such a huge devices to everywhere we go. Okay, that is size is the major drawback. Okay, size is the major drawback. So that's why in 1960s or 1970s, if we see the TVs or if we see the radios or if we see any electronic gadget, the size was big. Okay, they were in big size. The size was huge. That is the basic drawback. Okay, so that's why. So to overcome all these things, so we have to go for another technology. So that what investigations were made on FET. Okay, special. I am not discussing about JFET, all these things. What is important, what is required for you, that only I will discuss. Okay, so BJT also, no one is what if you go to any interview, so you should have some knowledge on BJT. Why MOS is more important than BJT? You should know. And what are the drawbacks with the bipolar junction transistors? You should know these things. That's why what I have given some glimpses of this BJT. So now we'll go for MOSFET. Okay. So size is the major drawback, and later on, as MOS came into existence, it was very what it has changed the era of electronics, or changed the era of semiconductors as MOS came into existence. So actually, this VLSI, one specialization, so it has been existed, and it is existing, and it will exist. And so more and more investigations, more and more research will keep on going. So just because of the beauty of VLSI is just because of the MOSFET. And see, let us discuss about the MOSFET. Do you have any things to be clarified? Do you have any doubts? Is it clear? Shall I go ahead? You can ping me if you if you can't speak, you can just put a message. You drop in the chat. Shall I go ahead? Okay, right. Thank you for your response. Okay. See. Uh, Now, okay, we'll talk about MOS. If you have any doubts, you can stop in the middle and you can ask me. So we'll discuss about MOSFET. Okay. So MOS, you know what is. See, if we are studying about VLSI, definitely you should know about the MOSFET. Okay, that is the concept. So MOSFET. Sorry. So what is actually MOS? Metal. Okay. Oxide. Semiconductor. Okay. So FET, you know, field effect transistor. Okay. So metal, if you see, this is a good conductor or bad conductor? Metal is a good conductor or bad conductor? Metal is a good conductor or bad conductor?
Good conductor.
Yes, metal is the good conductor. Just respond me, that's it. Okay. So let us make the session interactive. That's why. Oxide is a bad conductor. Okay. Oxide is bad conductor. And semiconductor, it is a partial, okay, partial conductor. So see the combination of a good conductor, bad conductor, and semiconductor. Okay, The combination of these three is nothing but MOS. Okay, so FET is field effect. You no, I need not stress on that. So metal oxide semiconductor. See, semiconductor. If we see the structure of the MOSFET, so the base is nothing but the semiconductor. Okay, the base is nothing but the semiconductor. So semiconductor, it may be germanium, or it may be silicon, or it may be gallium arsenide. Okay, there are many types of semiconductors. So normally trend means apart from germanium, or apart from silicon, or apart from gallium arsenide. Okay, silicon germanium semiconductor was there, which was very powerful. It is very advantageous in terms of there will be many factors like short circuits, etc. I'll be discussing you in further. So silicon germanium also one is investigation. It is a very good semiconductor which was the trend actually. Okay, so see, this is semiconductor is germanium, silicon, or gallium arsenide. On the semiconductor, we will be using semiconductor is the base actually. Okay, semiconductor is the base. Okay, without a semiconductor, we cannot what we cannot what we cannot even start. Okay, so let's start with the semiconductor. On the semiconductor only, we will be integrating all the components. Okay, on the semiconductor only, we will be integrating all the components. So I told you, right, whatever the active and passive components are there, or everything will be integrating on the semiconductor. So the basic things are transistors. Okay, so main things are the transistors. The transistors we will be forming on the semiconductor. Okay, next thing is if we talk about the oxide layer. So oxide layer, which is a bad conductor. So the semiconductor, I told you, it is a base. Oxide layer, it is used to isolate or separate the components. Okay. So and also oxide layer is called as a protection layer. Okay. It is it is used for isolation purpose, and oxide layer is used for the protection, protecting your IC. Protection purpose it will be used. Okay, isolation and protection. Okay, next one is, so apart from the oxide layer, there is a metal layer, right? Okay, metal layer is there. Metal layer, it is used for interconnections. Okay, if you are connecting many transistors, if let us suppose 10 transistors are on the semiconductor, so if you want to connect all the transistors, if you want to give the connections internally, so you will be using the metal layer, and for interconnection purpose, and also uh, interconnections, and also what we see, if you for the from supply, let us suppose from supply, if you want for your IC, if you want to what give some supply through the, you will be giving the supply directly to the metal. Okay, so wires as metal layer is used for interconnects and wires. Okay, interconnects and wires. So this is about metal oxide semiconductor. So if we see, so we have discussed about MOS also. So now we will see about the flavors of MOSFET. Okay, so as you know, MOS flavors are NMOS and PMOS. Okay, NMOS and PMOS. So in NMOS also, and we have, before going to that, NMOS and PMOS are there, right? So in NMOS and PMOS, so why it is called as NMOS ante N channel? The channel is of N type. and PMOS ante channel is of p-type. Okay, so to show you more clearly, okay, so I told you, right? So this is your semiconductor. Okay, semiconductor. For NMOS, the substrate will be of p-type. Okay, for PMOS, the substrate will be of n-type. Okay, so substrate will be of n-type. So, and you will be having MOS source and drain regions, right? I will be discussing MOS. So, three terminals of the MOSFET are gate. So, you will be having source, and this is the drain. Okay, gate, source, drain. These are the basic things. That's why I'm explaining you. So, see here, the for P type, let us suppose this is your source and this is your drain. Okay. So for a if the channel is of P type, the source will be of N type and drain also will be of N type. If you take an NMOS, the source will be of P type and drain also will be of P type. And whenever you are giving a supply, okay, for P type, if you are giving a supply, what happens? The channel will be formed. So the what from source region and from the drain region, so the carriers will be attracted here. The channel will be of source and drain are of N type, right? All the N type carriers will be attracted towards the gate. This is called as gate actually. Okay, this is the gate region, and the center one is gate. You need to give the supply voltage V in to this gate. Okay, you need to give the supply voltage V in to this gate. So whenever you are giving the supply voltage, so here for the N channel MOSFET, all the N type carriers from source and drain will be attracted towards the gate. And in the PMOS, what happens? The P charges will be attracted towards the gate if you are giving the supply voltage, V1 supply voltage. Okay, so this is about the N type MOSFET and P type MOSFET. And so, is it clear for all of you? Clear for all of you? If you have any doubts, you can just ask me. Okay, if it is clear, I'll go ahead.
Clear.
You don't have any doubts, huh? If you are not having any doubts, that means you are not understanding anything or you are concentrating somewhere else. So better be active and you should ask the doubts always. Okay. So NMOS and PMOS till here it is very clear for all of you. And next one is in NMOS and PMOS. Okay. So in NMOS and PMOS, at the end of the session, I'll be asking questions. Okay, on today's class, you get ready for that, and always insist you to write the notes, make the notes. Okay, make the notes. So NMOS and PMOS. In MOS, we have depletion mode MOSFET, and we have enhancement mode MOSFET. Enhancement. Okay, so here also in P type we have depletion and also enhancement. Okay, so what do you mean by depletion mode MOSFET and enhancement mode MOSFET? Can anyone can answer to this question? Do you know what is enhancement and depletion? So if you don't know, I will tell you. So MOS, okay, any MOS, if you take NMOS or PMOS, it will be of depletion and enhancement. These are the two flavors, two types, okay, depletion and enhancement. So I will write from this depletion. So depletion mode MOSFET, normally, if you see these, MOSFET, property, I will show you the difference. This is source and this is gate and this is drain. Okay, so here also you have source, this drain, this gate. This is drain and this is gate. So what is making the difference between depletion mode and enhancement mode MOSFET? Can you see the figures and tell me what is making the difference between depletion and enhancement mode MOSFET? Can you see the figures and can you tell me the difference? Anyone? You guys please respond. Otherwise, the contribution will be wasted. Just I'm asking a simple thing. These two figures you are seeing, right? These two figures you are seeing. What is the difference that you can see? So this is gate.
Depletion mode, some layer is found to gate.
You can see some layer in depletion mode MOSFET where it is not there in enhancement mode MOSFET. What is that layer actually? What is that layer actually? See, this layer, what you are seeing is nothing but this is the channel. Okay, ఈ black color ఏంటంటే this is the channel. Okay, so this is the channel. So there is no channel for the enhancement mode MOSFET. Okay, so here in depletion mode MOSFET లో ఏంటిదనంటే there will be an existing channel. Okay, during the fabrication, ఇది మనం fabricate చేసేటప్పుడే, so what happens, you will be fabricating the channel also. Okay, so you will be this is the prefabrication of the channel. Okay, so enhancement mode MOSFET, there is no channel. Okay, you can call this as a channeled device and this is a channelless device. Okay, this is the channelless device. Okay. So see here in depletion mode MOSFET, whenever you are giving the VIN input voltage ఎప్పుడు ఎక్కడ ఇవ్వాలి అంటే గేట్ దగ్గర ఇవ్వాలి. So whenever you are giving the VIN gate input voltage to the depletion mode MOSFET, what is happening? See, this channel may be N type or P type. Okay, so if you are giving some opposite voltage to this depletion mode MOSFET, this channel is getting deleted, eliminated, and the channel will be we can say channel will break. Okay, whenever you are giving the supply voltage, the channel will break. Whereas in enhancement mode MOSFET, whenever you are giving some input voltage to the enhancement mode MOSFET, if you are giving some input voltage, what is happened? Channel will be formed. Okay, channel will be formed. And one more thing is, so one see there one time the channel will break. Okay, once if the channel is broken in the depletion mode MOSFET by the application of the input voltage, what happens is it starts acting like enhancement mode once the channel is removed or broken. Once the channel is removed. Okay, once the channel is removed by the application of the input voltage, what happens is the depletion mode MOSFET will start acting like enhancement mode MOSFET. Okay, in general we will be using enhancement mode MOSFET only for all the fabrication. Whatever the ICs that you are fabricating, you will be using the enhancement mode MOSFET only. Okay, so depletion mode MOSFET wherever it is required. Okay, so wherever it is required, for NMOS only, NMOS enhancement ki opposite one is NMOS depletion. Okay, wherever it is required, you will be using the depletion mode MOSFET, but in general we will be using enhancement mode MOSFET only everywhere. Okay. So any doubts here in this particular page? Any doubts are there? Shall I go ahead? So what I have discussed is the BJT and MOSFET. Okay. So why BJT is, what are the drawbacks of BJT? I have told you. And why MOSFET is advantageous than BJT? I have told you. And why VLSI is more popular just because of MOSFET. In MOSFET we have NMOS and PMOS. NMOS, PMOS low, there are still depletion and enhancement mode MOSFET. So the differences between depletion and enhancement mode MOSFET also I have told you till here. Do you have any doubt till here? So do you want me to go ahead? Do you want me to go ahead?
Yes, ma'am. Continue.
Yes, yes. So this depletion and enhancement mode MOSFET we have discussed. Now clearly, one point before that. So I will tell you the differences between BJT and MOS. So first thing is size is a drawback. Okay, size is more, and here MOS devices less size and a compact. Okay, so MOS devices are compact. Second thing is power consumption will be more. Power consumption is more. Next, ఇక్కడ less power consumption or low power consumption. Okay, low power consumption. So next one is third one ఏంటిదనంటే so high drivability. High drivability means I will tell you. High drivability, less drivability, and this is speed is more, and less speed, no, less speed. Okay. So what there are still many advantages of MOSFET also compared to BJT. Why don't we prefer BJT? Size is more and power consumption is more. Okay. So these are the advantages: high drivability and high speed. BJT is a high speed circuit. And coming to MOS is a compact device, so it consumes very less amount of power. Okay, drivability is very less. What do you mean by drivability? So the whatever the with the output, this is the input. Okay, if you take this as a BJT device, so this is the input. Okay, so it is producing some output voltage. With this output voltage, you are able to drive one more load. Okay, so it is having the capacity to drive the other circuit also. With the output of this circuit, you can drive one more load. With the output of this circuit, you can drive one more load. This is what is called as drivability. The drivability of BJT is more. Okay, speed is also more. But whereas MOSFET, if you see, if you take a MOSFET, if you are connecting any other device to the output of the MOSFET device, it may not drive this device. Why? Because here there will be lot of voltage drop here, so it cannot. The capacity is very less to drive the other circuit. Okay, so these are the differences between BJT and MOS. And next thing is uh, coming to the what? If we talk about MOSFET only, the MOSFET lone, so it will operate in three regions. One is what? Uh, uh, active region. Active region. So first one is cutoff. Cutoff, active, and saturation region. Okay, cutoff, active and saturation region. Okay, I will show you clearly what is cutoff active. Din tarvata we will go to the actual topic. Okay, so see, if you take a MOSFET, okay, you need to know about the operation also. This is also one very important thing. Okay, even if you are into digital, uh, interviewers may be asking you, not maybe, interviewers will ask you. This is a basic thing. They will ask you about the operation also, especially the freshers. You should know. Okay, so source, and this is our semiconductor. So this is drain, and here is our gate. Okay, so you need to give the V in. Okay, so actually there will be a threshold for the gate that is called as VGS. Always when the channel is formed, ఇక్కడ ఛానల్ ఎప్పుడు ఫామ్ అవుతుంది అంటే ఛానల్ విల్ బి ఫార్మ్డ్ when Vin is greater than VGS. Okay, Vin is greater than VGS. This is enhancement mode MOSFET. Vin is greater than VGS. Channel is formed. Okay, channel is formed when Vin is greater than VGS. So ఇక్కడ VGS is the just the channel will be formed, but the MOSFET will operate whenever we are giving the supply voltage, which is called as VDS. Okay, whenever we are giving VDS, which is called as the supply voltage, then only the MOSFET will start operating. So first condition is this VDS is there, right? VDS is equal to 0. I am not giving any voltage to this. I am not giving any voltage to this drain. VDS is equal to 0. So this is in this condition. Okay, in this condition, this is second one is VDS. Three conditions are there. VD. First condition, VDS is equal to 0. So here only the channel is formed. Channel is formed, no, but no conduction. Okay, no conduction will take place. Only channel ఎప్పుడు form అవుతుంది when the channel is formed. Only whenever we are giving V in, channel is formed, but there is no conduction. Why? Because drain to VDS, drain to source voltage is equal to 0. Okay, in second condition, so second condition for all the conditions, okay, this should be must and should for all the condition. In second condition, VDS is less than VGS minus V. Sorry, just you have to excuse me for one reason. Why? Because the this is VGS, input voltage is VGS. So gate is having some threshold voltage that is called as VT. Why? Because for silicon or germanium, we are having cut-in voltages, right? 0.7, 2 like that, 0.3 like that. So gate is having from some threshold voltage. Sorry, for all the condition, VGS should be greater than VT. Okay, VGS should be greater than VT. So VDS is less than VGS minus VT. This is called as the operating voltage. Okay, operating voltage. ఈ కండిషన్ లో దట్ మీన్స్ స్లైట్లీ ఐఎమ్ ఇంక్రీజింగ్ దిస్ వన్. ఇది నేను కొంచెం VDS నేను వాట్ ఇఫ్ ఐఎమ్ ఇంక్రీజింగ్ దిస్ VDS slightly, I have raised this VDS. Slightly I have raised this VDS. At this condition, what happens is, so the channel will become thin at this end. Drain end దగ్గర channel will become thin. Why? Because let us suppose this is NMOS. So negative charge carriers are flowing here. So let us suppose, listen very clearly, this concept is important. So there are negative charge carriers here in this channel. Okay, why the channel will become thin here at the drain side means VDS is the positive voltage which you are giving. What is happening? The as we are giving the positive voltages, the negative charges are attracted towards this positive voltage. Okay, here the channel will become thin. Okay, but still the path will be existing from source to drain. Okay, there will be a path from source to drain. So path path will be there. Okay, path will be existing from source to drain. Path will be existing from source to drain, and also conduction will be taking place. Conduction will be there, and here what is happening is the current flowing in the MOSFET. So what current flowing is nothing but IDS. So IDS will be increasing. IDS increases with respect to V. Ante however we are increasing this voltage, IDS will be increased. Okay, so this is one thing. VDS ante chudandi, in the first case what happens, so this is VDS, this is IDS. Okay, so నేను ఏం చేస్తాను, in first case లో VDS is equal to 0 దగ్గర there will be no conduction. Let us suppose if we are increasing the VDS, as I am increasing the VDS, what is happening? The current will start increasing. And the last condition, VDS greater than VGS minus VT. Okay, this is the third condition. The third condition lo emoutundi anante, as the voltage, positive voltage at the drain side is more and more, what will happen is the channel will be pinched off at the drain end. ఇక్కడ ఏమవుతుంది అని అంటే the channel will be pinched off at the drain end. Okay, as the channel is pinched off at the drain end, the current will become constant here. Okay, so దీన్ని ఏమంటారంటే resistive region. Okay, resistive region. The second one is called as resistive region. Okay, second one is resistive region, or it is called as ohmic region. Okay, ohmic region అయినా అనొచ్చు, resistive region అయినా అనొచ్చు, or else we can call it as an active region. So active region లో this is the active region. Active region అంటే, so current will increase with respect to the voltage. It is called as active region. Okay, and this is the saturation region. Current is becoming constant. మీరు ఎంత VDS increase చేసినా, so current is becoming constant, saturation. And this is the cutoff region. Cutoff region ante there is no current conduction. That is the that is the cutoff region. Ikkada everything has become very untidy. Clearly I will so you know the figure now. ఏంటిదనంటే VDS అంటే ఇక్కడ డ్రైన్ కి ఇచ్చే వోల్టేజ్. Okay, this is the VDS. So as this VDS is increasing, VDS is equal to 0 దగ్గర, this is cut off. And here as VDS, so in this region VDS is less than VGS minus VT ante VGS minus VT, this is the active region. Okay, active region or ohmic region, or this is the resistive region also, we can call it as resistive region. So wherever the current is becoming constant, okay, this is called as saturation region. In saturation region, VDS is greater than VGS minus VT. Okay, these are the three conditions. Normally the MOSFET will act as an amplifier in active region. Listen to me carefully. MOSFET will act as an amplifier in active region. In saturation and cutoff region, it will act as a switch. Okay, so we will be, and for digital logic design, so we will only the saturation region and cutoff region only we will be considering. Okay, for digital logic design. This is about the theory of the MOSFET, which is part of VLSI. And so till here, is it clear for you the operation of the MOSFET? Till here it is clear for you? Are you getting confused or is everything clear for you? You simply don't say yes. You should ask me the doubts. Ashok, can you unmute yourself? Ashok, can you unmute yourself? And Nagara, okay, Ashok, okay. Is it clear for you?
Madam, this is totally new, thinking like new subject now. So little bit confusion is there.
Confusion is there. Where are you getting confused?
Right now it seems everything is okay,
Mhm.
but somewhat confusion is there. Not exactly where it was.
Okay.
Can-
See, what definitely, what after a long gap you are looking at the subject once again. So there will be, if there is a confusion, I'm always here to explain you once again. But the thing is, these are the basic things. Chudandi, if you see the syllabus, these are, you cannot, all these MOSFET basics, all these things. If all these things, I need, these are not included in your syllabus. But the thing is, what you should know, okay, what you require. I am starting from the scratch actually. Meeku MOSFET basics తెలియంది you cannot go for VLSI. Why because this is like a heart. Okay, మీరు you should know the active region, saturation and cutoff region. So on what conditions it is operating in these three regions, you should know. Okay. And digital electronics ki velle mundu, before going to the digital electronics, so we should take two conditions of operation. అది ఏంటిదంటే కట్ ఆఫ్ అండ్ సాచురేషన్ లో MOSFET ఆపరేట్ అవుతుంది. So after knowing these two conditions only, we can go ahead. So um, I think, do you want me to explain the regions? Let me ask you I will start with the sequence actually. So,
regions is okay, ma'am. You say VDS is greater than VGS.
okay.
Yes,
Oh,
all
oh,
those things are very confusing.
very confusing, right? Yes.
When you said that VDS equal to 0, that is in a cutoff region, and
Uh,
with increasing of VDS, IDS also increasing, that is a active region.
mm,
When it is a stable means that is a what is saturation region.
yeah.
This theory part is okay, but when it comes to VGS is greater than like statement, that was confusing.
Okay. Actually, I thought ఇది మీకు కొంచెం feedback ఇది ఇవ్వాలి. Some input is needed. Let me share the screen. So very good. You should ask me why, because I also feel good if you ask me. Simply, if I keep on talking and if I, it's a waste of contribution if I cannot make the session interactive. So let me share the screen again. Okay, so see here. So with this figure only we can analyze. Okay, so this is source, this is drain, and this is gate. Okay, so source is always grounded. Okay, I'm taking NMOS. Okay. So I'm taking NMOS. NMOS and ante. So here you will be having N-type electrons. These are the N-type electrons. And P-type semiconductor. Okay, P-type semiconductor. So source you are grounding. This is NMOS. Okay, which type? Enhancement type I'm taking. So this is VDS, and this is the VGS is the input voltage. Okay, input. VGS, why we are calling it as VGS means for the gate we are giving, that's why it is called as VGS. So VGS is the input voltage, and gate always will be having some threshold voltage. Okay, gate always will be having some threshold voltage. Always the channel will be formed. When the channel will be formed? When VGS is greater than VT. Whenever, student, even if you take a diode also, if you take silicon diode, once if the voltage is reaching the cut 0.7 cut in voltage, then only the diode will start conducting. Here also, for this, there is a threshold voltage. It may be anything depending upon the size of the semiconductor. So VGS, the channel will be formed only when VGS is greater than VT. This is the first condition. And second condition is, so channel is formed when VGS is equal to VT. VDS is equal to 0. This drain, this is called as the supply voltage. This is the supply which we are giving to the drain. Okay, if you see the MOSFET, if you see the structure of the MOSFET, it will be like this, right? This is the gate, and this is drain, and this is source. Source we are grounding, from the drain we are taking the output. Okay, so gate input voltage we are giving so that the channel is formed, and first initial condition is VDS is equal to 0. Whenever we are not giving any supply voltage, that's why diode will be cut off. No conduction. Okay, this is clear. Next one is, see, I told you VGS greater than VT, then only the channel is formed. So actually, whatever the input voltage is there, we need to minus the threshold from the input voltage. Okay, this will be the operating voltage. Okay, with this much of VGS minus VT operating voltage only, what happens? The the channel will be formed. Okay, this is called as operating voltage. So whatever the input voltage is there, you should minus the operating voltage. Okay, so this is what is called as VGS minus VT. So in the second condition, if we see VDS, the supply voltage is less than VGS. Okay, is less than VGS. Okay, less than VGS. Only thing is, you are minusing the threshold, you are removing of the threshold voltage. Okay, this is the operating voltage. So in this condition, what will happen? As you are giving the so slowly you are raising. You are giving the VDS, but very small voltage you are giving. With this very small voltage, what is happening? The carriers are negative charged carriers. Negative charged carriers at the drain, ఇక్కడ supply voltage మీరు ఇస్తున్నారు కదా, what is happening at the drain end, the channel will become thin. There will be a path, there will be a conducting path, but only the thing is, the negative carriers are attracted towards this positive supply which we are giving, but there will be conduction. The MOSFET, what will happen? So as the MOSFET will work in what? The MOSFET will act as an amplifier. That means it will act in, this is called as active region. In active region, as we are slowly raising the VDS, what is happening? The current also will start flowing in the MOSFET. From drain to source, the current will flow. Okay. So this is called as active region. Third one is, if you see for VDS also there is a limit. Okay, you cannot go beyond the limit. So VDS, if it is greater than this VGS, if this VDS voltage, if it is greater than the input voltage, minus this threshold. Always you should minus the threshold, that is common. If it is going beyond this input voltage, what happens? More and more carriers, more and more negative charge carriers will be attracted towards the attracted towards the uh, attracted towards the drain side. What will happen? The channel will be pinched off here. There will be no channel. ikkadunna negative carriers anni kuda, so they will be attracted towards the positive side. The current will become constant here. Okay, the current will become constant. Okay, is it clear now? Is it clear now, Ashok?
Yes, ma'am.
Okay. So see, if you are not able to catch up, or if you are not able to understand, you can always I'm in the group, right? You can always ping me, or you can always call me, so that I can explain you. Okay. So this is and how about others? Are you getting confused? Nagaraju, can you unmute yourself? Nagaraju, can you unmute yourself? Or it's Ganesh, can you unmute yourself and you can you talk?
అర్థమవుతుందా?
అర్థమైందా? So that is what. Okay. So this is about we will be taking only two conditions ఏంటంటే for digital electronics, or for the digital design of the digital circuits, we will be considering the MOS only in what we say two regions. ఏంటిది? అది cutoff, and next one is saturation. Okay, cutoff and saturation. So why? Because we digital electronics antene nothing but like 101010 concept. On 101010 concept we will be the whole digital electronics will be running. So that is nothing but the switch. So if you want to use your MOSFET as amplifier, so it should operate in active region. Okay, so this is about. So next thing is more ASIC design flow is there. Design flow. So we will be discussing about ASIC design flow tomorrow. So now if we see the fabrication of this VLSI circuits, first we will start with the semiconductor. Again we'll go with oxidation, tarvata photolithography, and lithography ante it is called as masking techniques. You can refer any textbook. Just this is not a part of our syllabus. So just to give an idea, lithography, tarvata masking is nothing but lithography, and forming of what source drain regions. After the formation of source and drain regions, what you will be doing, interconnections, metallization. Okay, all these things you will be doing, you will be going. You can refer any textbook, or you can Google it if you want to have the information, but this is not a part of our syllabus. Just okay, you should know about the fabrication details also. But next thing is, so ASIC design flow is very important. Okay, ASIC design. So normally, so in VLSI, we have front end and back end. Front end and back end. So front end is nothing but what RTL coding. You have to do the RTL code. That means designing any circuit. You will be using Verilog and or VHDL, and you will be writing the code for any circuit. Let us suppose if you have to design an simple example adder. If you want to design, what you need to do, first thing is you need to write a RTL code for the adder. After writing the RTL code, what you need to do, you need to simulate. After simulation, you need to do the synthesis. Okay, After synthesis, what you need to do, you will get the gate level netlist. Okay, then again you will be doing the timing analysis, and the next one is power analysis. All these things I will be showing you with the help of PPT or image tomorrow. So I have an image actually. Let me tomorrow briefly I will explain. But only thing is, just if I show you, uh, if I show you that slide, it will be helpful for you. See. So if you see this figure, are you able to see the flow chart? Flow chart వస్తుందా ఇంకా వేరే ఏదైనా వస్తుందా? Flow chart, are you able to see? Design specification, behavioral description. Okay. Okay, this is the flow chart actually. So this is also not the detailed flow chart. If I give you the detailed flow chart, it will be many steps starting from the design specification only tape out varaku. There will be number of steps. Okay, number of steps. But we will see. As first thing is, if you want to design any digital circuit, if you want to design any digital circuit, you need the specifications. Okay, let us suppose if Samsung fellow, if we want to mm, if we want to introduce a new mobile with new concept, what he has to do is he need to give the design specification to a particular vendor. Okay, so that particular vendor, he will be writing, he will be giving the distributing the work to and other what uh, other fellows like Intel, or some part of the work he will be giving to Qualcomm, or some part of some IC he will be giving to what AMD, like that. In a mobile we'll be having, in an electronic gadget we'll be having different chips. Okay, so each and all the chips are not designed by only one company. That work will be distributed to other companies. Okay, first thing is mm, I want to have I want to have the design and device according to my specifications. So the thing is, I will give design specifications. Okay, I'll give my requirements actually. So the vendor will write the specifications, and then after writing the specifications, I told you, right, adder, I want to design an adder. So after writing the specifications means the device has to operate with this much of frequency. The device should have these many inputs, and the outputs. What are the inputs and what are the outputs? How much frequency, on how much frequency it has to run, and what should be the clock speed, and what is the power consumption, what is the power dissipation. All these things you will be describing. That is what is called as design specifications. And behavioral description, that means you will be writing the RTL code. You will be describing the behavior of that circuit. So here you will be writing the HDL code. It may be in Verilog, or it may be in VHDL, or it may be, so anything Verilog or VHDL only for this digital design. So RTL description, RTL engineers, RTL designer, there will be a role of RTL designers in many VLSI companies, right? So so and so company is hiring for RTL designers. The RTL designer's role is just writing the Verilog code, okay, for any particular design. Next one is after they have written the code, what TFT engineers, what they will do, testing of that code will be done. Okay, whatever the Verilog program you have written for a specific adder, the testing will be done. Okay, functional verification will be done. Whether whether for specific set of inputs are you able to get the proper outputs or not, that is the functional verification. Let us suppose 8-bit adder means you will be giving different combinations of inputs. So for that particular combination of inputs, you should get the expected output. Okay, that is what is called as functional verification. And you will be testing your the code. Okay, you will be testing your code. Okay, this is software, in software only. And next one is you will do the, see, getting the output is not important thing, but you should get the output on time. That is what is called as timing verification. So after synthesis is nothing but converting your code into circuit. Converting the code into circuit it is called as synthesis. That is, after synthesis you will obtain a gate level netlist. Okay, gate level netlist will contain lot of information. I will tell you tomorrow. I will give the detailed description of this gate level netlist. Tarvata, again you have to do the logical verification and testing. After testing, what you have to do is you have to do the floor planning. See, required area is only what x by z mm. Okay, in that x by z or 2 what is that 2 m by 2 mm, in that particular area you have to fix your IC. Okay, you have to fix your IC. So that is what is called as floor planning. After floor planning, you will be uh, you after floor planning you will be doing the routing and placement. Okay, placement and routing you will be doing. Placement is nothing but placing all your components in that particular what in this particular given platform or in that particular floor. And you should route. Okay, you should give the interconnection between all the components. That is what is called as routing. Then physical layout verification, implementation. ఇక్కడ నుండి అంత బ్యాక్ ఎండ్ అన్నమాట. సో జస్ట్ I have given you the glance. Tomorrow we will be discussing completely on this ASIC design only. So each and every small detail or big detail, so we should understand it very clearly. So we will discuss this starting from the specifications. In this particular ఈ బాక్స్ కదా design specifications లో what are the specifications we have to take. We will take an example and we will be discussing on that. So on each and every block I will be giving you detailed information. So let's close the session for today, and I will stop here. Okay. Did you learn anything today? Did you learn anything today? Hmm? What did you learn? You just tell me what did you learn. At least I'm expecting three points from each one of you. Ashok, Nagaraju, and Ganesh. I will leave you then. Okay. So we'll start with Nagaraju. Are you there? Nagaraju, are you there? Ganesh, are you there? Please respond.
Yes, ma'am.
Yeah. Tell me any 3 points from today's class which we have discussed.
Starting BJT onwards, we are starting. BJT సైజ్ వల్ల డిస్అడ్వాంటేజ్ మేడం. స్పీడ్ పరంగా పెర్ఫార్మెన్స్ బానే ఉంది.
MOSFET ఎందుకు ప్రిఫర్ చేస్తాము? MOSFET ఎందుకు ప్రిఫర్ చేస్తాము?
MOSFET సైజ్ చిన్నది మేడం. పవర్ కన్జంప్షన్ లెస్.
ఓకే.
ఆ రెండు వల్ల
వెరీ గుడ్, వెరీ గుడ్. అండ్ వన్ మోర్ పాయింట్ యు టెల్.
అంటే అడ్వాంటేజ్ మేడం.
Not advantages. So any what is the difference between enhancement and depletion mode MOSFET?
ఛానల్ ప్రీ ఫ్యాబ్రికేటెడ్ గా డిప్లీషన్ లో ఉంటుంది మేడం. అదే ఎన్హాన్స్మెంట్ లో ఛానల్ తర్వాత క్రియేట్ అవుతుంది.
ఓకే, ఓకే. సో ఛానల్ వన్స్ బ్రేక్ అయిపోయిన తర్వాత డిప్లీషన్ మోడ్ మాస్ఫెట్ ఎలా యాక్ట్ చేస్తుంది?
ఎన్హాన్సన్ మోడ్ దీనిలో పనిచేస్తుంది.
వెరీ గుడ్, వెరీ గుడ్, వెరీ గుడ్. అశోక్, కెన్ యూ అన్మ్యూట్ యువర్ సెల్ఫ్? ఓకే. సో can you tell me the regions of operations?
There's 3 regions, ma'am. One is cutoff region, and other one is active region, and the last one is saturation region. When VDS is equals to 0, that is in of cutoff region. When IDS is increasing depending on VDS, that is an active mode, active region. And when VDS and IDS are null, means there is no change in that region, that is a saturation region.
If VDS is increased beyond the limit, what happens? The channel will pinch it off. Okay, pinch it off. There is no flow.
There is no path between source and drain.
Current will become constant. That's it. Okay.
That's it. And in active region, it acts like as amplifier. In cutoff region and saturation region, it acts like as a switch.
For digital electronics, the switch operation only we require. Okay. So these things you remember and revise. Tomorrow we will be discussing on ASIC design flow completely. Okay. We will end the session. I don't know what is the problem with Nagaraju. He has muted.
Madam, always which one we prefer, P-type or N-type?
What? Yeah, this is also very important. But N-type only we will prefer. Okay, N-type ఎందుకు ప్రిఫర్ చేస్తాము అని అంటే, see, P-type channel if we take PMOS తీసుకుంటే, so majority charge holes.
Channel create అయి ఉంటుంది. ఆల్రెడీ ఛానల్ క్రియేట్ అయి ఉంటుంది. అందుకని P-type మనం ప్రిఫర్ చేస్తాం.
No, ఆల్రెడీ ఛానల్ క్రియేట్ అయింది దేంట్లో? డిప్లీషన్ మోడ్ మాస్ఫెట్ లో. డిప్లీషన్ మోడ్ మాస్ఫెట్ అవసరం ఉన్న చోట ఎక్కడో ఒక దగ్గర యూజ్ చేస్తారు, whenever it is needed. But all the digital circuits we will be using enhancement mode MOSFET only. అది కూడా N type. Okay, N type ఎందుకు యూజ్ చేస్తారు అని అంటే, see what P-type if you are using P-type majority charge carriers are holes. Okay, so majority charge carriers holes kabatti the mobility of holes is 3 times less than mobility of electrons. Okay, అర్థమైందా? అందుకనే హోల్స్ మొబిలిటీ తక్కువ ఉంటుంది కాబట్టి పీ ఛానల్ డివైజెస్ స్లోగా ఉంటాయి. ఓకే, దట్స్ వై వి ప్రిఫర్ ఎన్ ఛానల్ మాస్ఫెట్స్. ఓకే, am I making you confused? Is it clear?
Clear ma'am. P-type లో హోల్స్ ఉంటాయి. P-type లో హోల్స్ ఉంటాయి కాబట్టి అక్కడ కమ్యూనికేషన్ అనేది డిలే అవుతుంది.
Yes. Okay.
ఇక్కడ N-type లో ఎలక్ట్రాన్స్ ఉంటాయి కాబట్టి 3 times ఫాస్టర్ గా పనిచేసి కమ్యూనికేషన్ ఫాస్ట్.
Yes. సో యాక్చువల్గా ఏంటిదంటే N-type లో కూడా డ్రాబ్యాక్ ఉంటుంది. ఏంటి అని అంటే, షార్ట్ సర్క్యూట్ ఆల్వేస్ పవర్ సప్లై ఎక్కువ అవసరం. అండ్ వన్ మోర్ థింగ్ ఇస్ ఈజీగా షార్ట్ సర్క్యూట్స్ అయితే N-type ట్రాన్సిస్టర్స్, NMOSFETs. Why? Because constant మనము maximum voltage ఇచ్చినప్పుడే NMOS ఆన్ అవుతుంది కాబట్టి so what happens is it continuously requires supply and heat dissipation will be more for NMOS. So PMOS కి drawback ఉంది, NMOS కి drawback ఉంది, అందుకనే we will be going for CMOS. Okay, CMOS is combination of N and P. Okay, that in depth if we go there is lot more theory. So but the thing is, if you want I will share the what sufficient material. I have enough material, I will share with you. But today introduction lo ivi kuda తెలియకుంటే problem అవుతది అని I have given you. So if you need extra information, definitely I will give you. Okay, in the class I will be sharing only what I will be explaining on. I will be going according to our syllabus. Okay.
Okay.
Shall we close the session?
Right.
Okay. Thank you. Thank you.
Thank you. Thank you.